Up to this point, we've been looking at the molecular partition function, and we can separate, again, as mentioned previously, you can separate the total partition function into these different parts with the different energies. So we've looked at the translational partition function, we've looked at the electronic partition function, and in this video, we're going to look at the next, which is the vibrational partition function. We are only, in our class, we're only going to consider diatomic molecules that only have one vibrational motion. If you have a polyatomic molecule, you'll have many vibrational modes, and you would need to consider each of those vibrational modes. But we're just looking at one vibrational mode for this class, since this is just an introduction. And our model that we're going to use is we will imagine our diatomic molecule has a bond that looks like a spring. And we can solve this problem via quantum mechanics to get the energy levels associated with this model. It's called the harmonic oscillator. And we have an energy that depends on a quantum number called V. And the energy is equal to h, Planck's constant, times this constant, nu, which is not a V. It looks a lot like a V, but this is nu, times V, which is our quantum number, plus a half. Okay, and so this constant nu is equal to the square root of k over mu times 2 pi. And k here is the force constant of the bond. This would be the spring constant if this was actually a spring instead of a bond. And this is roughly tells us, how strong is the bond. And then mu, this letter here, this is the reduced mass, which is given by a particular formula, which is equal to m1 times n2 over m1 plus m2. And then v here, our quantum number, can take specific values. It's an integer ranging from 0 up to, in theory, infinity. Okay, and this describes the vibrational energy levels of a diatomic molecule. To a first approximation. This is under the harmonic approximation, and we won't get into more details, but there is anharmonic effects that you have to worry about if you want to more accurately model this. But we're just going to consider just the harmonic approximation, and this is our energy levels associated with vibration. Okay, and so, and just in terms of units, so this version written here, or the vibrational frequency nu, this is often given in units of wave numbers. The way I have it written now, it wouldn't be, but so nu is called the vibrational frequency. And this is if you, for example, measure the vibration of a diatomic or a polyatomic molecule, this is what you would observe via infrared spectroscopy. You'd see these vibrations. So something like a CO stretch or something that you would observe, or CC stretch or OH stretch. These are vibrational motions that you can observe via infrared spectroscopy. Okay, so given that we need to find what's the partition function, right? That's what we're after, is what's Q vibe. And so just by definition here, we need to add up all these different energy levels. So we start at V equals 0 up to infinity. Our exponential term, there's no degeneracy we need to worry about with the vibrational frequencies. They're all singly degenerate. So we get e to the minus beta times this energy. So we get h times nu times v plus a half. All right, and so this is our partition function. But then the next question is, can we express this in a simpler form? Now, what we did with the translational partition function is we said, oh, well, we can approximate this sum as an integral and then solve it that way. With the electronic partition function, we said, oh, there's only going to be a few terms. We can just evaluate those manually. And for the vibrational partition function, it turns out we can rearrange this sum and get an exact answer. There's an analytic expression to this, so there's no approximations necessary here, as long as it follows this equation up here. As long as this equation holds, then the value we're going to get is right. There's no approximation necessary. All right. Well, the first thing we can do is separate out this exponential into two parts. So we have one part that will have a v in it and one part that doesn't, right? The 1/2 if we distribute this. So we will get an e to the minus beta h nu times v, because that's not confusing. And then we can separate also out a e to the minus beta h nu times 1/2. Right, so this is just separating out these two exponential terms. And since this second term has no v, it's just a constant that we can pull outside of the sum. Right, the sum is not adding up this term. This is just going to multiply by all the terms in the sum. So we can then say this is e to the minus beta h nu over 2. Just slightly rearranging how this looks. And we still have this sum from v equals 0 to infinity of e to the minus beta h nu times v. Now this sum here, this series, this is a geometric series. This has a known solution from mathematics. If we have a generic sum going from n equals 0 to infinity of x raised to the n power, this is equal to 1 over 1 minus x. Right, so this is a known solution from mathematics, and that's exactly what we have here. We have, right here, this is our x here is e, and our power here is minus beta h nu times v. Okay, so we can apply that. And what we need to do actually here is our x is not e. Our x is everything but the v. So that's our x, and our n is equivalent to v. Sorry, misspoke first. So we can go ahead and apply that, and we will have e to the minus beta h nu over 2 times 1 over 1 minus x, 1 over 1 minus e to the minus beta h nu. Okay, and this is our vibrational partition function. This is the final form that we get for this. So we'll go ahead and pause here, and in the next video look at some of the consequences or what we can do with this partition function, some more information we can get out of it.